So we are going to solve this example from your book, Griffiths' third edition on quantum mechanics, which is the example 2.4. So what they ask there is find the first excited state of the harmonic oscillator. Remember that we already have the ground state. So let's write the ground state here because we'll need it. And so this is the ground state already normalized. So this is the normalization factor. It's an exponential. That's why or Gaussian, sorry. That's why we said that it's such an important learning about Gaussians and Gaussian integrals is so important. Okay. Now, how are we going to find the first excited state? Well, the idea is to apply that A plus on that ground state. So applying that, we are going to get our first excited state. We just have to, at the end, check that it's really normalized. Okay, so that's what we are going to do. Now, what is this A plus? The A plus, let's remind ourselves, the A plus is that operator that we introduced, the raising operator, that is written as minus IP plus M omega X, and it has this square root, 2M H bar omega. Okay. Well, what does that mean? Remember that P here is the momentum operator, H bar over I ddx, correct? So this A plus means minus H bar and this derivative plus M omega X and that denominator. So that's what we need to apply on our ground state to obtain the first excited state. All right, so let's do that. So we are trying to find the psi1. This is some constant, some normalizing constant that we'll have to find at the end. We have, let me put this constant here. Then we have the part involving the derivative of that exponential, or the Gaussian function. Let's write everything, and then we start solve. So here's just a constant. Look at up there, is that normalizing factor for the ground state. And then here is exponential with x squared. So this is a Gaussian function. This is what we need to do. So it's pure derivative. No? At this point, it's not physics anymore, it's math. How do we continue? Well, let me put here in front all of these constants that we have. Right, so we have this M omega. And let's now go with the derivative. Well, the derivative there is that minus h bar, I'll keep that. And let's do the derivative of this part here. We'll get minus 2m omega x divided by 2h bar. Yeah? So what I did is the derivative of this part and the exponential that survives. And we also have this term here. So let me write this term here before writing the exponential. Okay, so do it yourself to be sure that you follow everything. Now let's see what we can simplify in this story. Well, this minus sign becomes plus. This h bar disappear. These two disappear. And you see that we ended up with a term that is just like that. And so we simplified things a lot. Yeah? So 2m h bar omega, m omega pi h bar omega, h bar 1/4. And what we got from that, 2m omega x, and that exponential with x squared. All right, that's where we arrived. Let's see. This this term here and this term here, they are pretty similar. Well, we can rewrite them so to try to simplify things a little bit. So how about we do the following? Look. There is 2 in the denominator and square root of 2 in the numerator. No? So we have something like this. If I multiply top and bottom by this, what we get is just square root of 2. And I'm going to do this to all the other terms. Okay, so by doing this, what we get? At the top, we have 2m omega, because it's the same terms that appear in the denominator and the square root. And below, the h bar. And that a square root. And the x is outside. Okay, so this is our first excited state. The only thing that remains is, well, what is this normalizing factor? And we have to go for the normalization procedure, which is picking this state that we found and checking that it's really 1, right? So, okay, so let's go on. We have that constant that we are trying to find. There are many other constants that I'll put outside the integral. M omega pi h bar half now, because so it was the squared. Then 2m omega h bar. And then the thing that we cannot get rid of, which is the terms that depend on x. Squared everything, right? Because we have this squared here. So here just h bar, right? Because it's because of the square. And we have to solve this integral. Okay, remember how we solve these integrals? We discussed that a very easy way to remember is when we have an integral like this, we can rewrite that as this derivative of this integral that we know very well how to solve, right? We talked about this in class. And what does that mean? If you solve all that, it means that we are going to get 1/2 of pi and whatever we have here, cube inside the square root. Yeah, we already talked about this, so this is what I'm going to do to solve that integral. All right, so let's continue. Here we have the a1 square, m omega pi h bar, square root of all that, 2m omega h bar, and now comes that solution. So we have the 1/2. Now let's put many things in that square root. So we have pi. Below we have m omega, all that cubed, which means square in itself, right? So m omega, I'll put the cube everywhere. Okay. All right. And you will see that many things now will simplify. Let's see what will simplify. We have here this factor 2, right? Let me rewrite and it will be clear to you. Let me rewrite everything that provided here. Okay, so this, for example, now the h bar cubed, that means h bar square multiplied by h bar, but h bar square gets out of the square root. So I'm going to take out of the square root h bar m omega, and what survives inside is the h bar m omega. Okay, and you will see now that many things will cancel, isn't it true? Look at this whole term and this one. One is the inverse of the other, gone. And now let's look at this this one and this one. One is the inverse of the other. So you see, everything simplified, and we actually now find that that normalizing constant is really just one. It's we were lucky, okay? So let me just write the psi1, the first excited state at the end, that A1 is really just one. So this is the solution for this exercise. Now this example, let me just write and then we talk. So what appear here is the X, and then we have the Gaussian part. So this is the solution of the problem of this example 2.4. We were very lucky that this normalizing factor at the end was just one. But if you try to go to higher levels, to second excited state and so on, you'll see that things become more tedious, and this normalizing factor will not be as simple as that. It's not going to be one, it will be more complicated. So an example that you should try to check, well, just to get a sense of how things become more complicated, is the problem 2.10. Question A is, okay, now that you find this psi1, construct a psi2. Okay, so how are you going to do that? Same story as we did above, but now you apply this A plus on the psi1 and check its normalizing factor. Okay, so the procedure is the same, but it's a little bit tedious.